We are going to analyze a clip from the first Avengers movie. Here it is.
You will all fall before me. Boy! Boy!
To find the velocity that Tony is thrown through the glass at, I used a ratio comprising of his height as a scale, and found the distance between him and the window to be 0.747 meters. And so to find the velocity of him crashing through the glass, I found his t to be 0.29 seconds, and then I plugged that into the equation of v is equal to delta x over t, with delta x being 0.747 and t being 0.29, and I got 2.5 meters per second. So by the time the suit catches up to him, Tony has fallen a distance of 1,147 meters. And we get that by plugging in the delta y is equal to 1/2 at squared plus v naught t. And we can assume his y velocity to be 0 at the start. So then we just have his acceleration of 9.8, and then the time of 15.3 seconds of when the suit actually catches up to him. So if we plug that in, we get 1,147 meters. The velocity that he's going at when the suit actually catches up to him is 150 meters per second. If we plug that into our v is equal to at plus v naught equation, we're still assuming v naught to be 0, and we just plug in 9.8 for a for acceleration, and then 15.3 seconds for t, and we get approximately 150 meters per second. For the suit to catch Tony at that height and him going at that speed, the suit needs to accelerate 28 meters per second squared. We get that by plugging in our 1,147 meters into our delta y, and that's equal to one half of the acceleration times the time it takes the suit to catch up to him. The suit stops propelling at 9 seconds, and so that's the time we use. And then we just set a is equal to 2 over 1,147 meters over 81 seconds squared, and then we get 28 meters per second squared. When Tony's suit starts to propel, he's fallen a total of 23 seconds. And if we plug that into our v is equal to at plus v naught equation, still assuming v naught to be 0, and we do 9.8 times 23, we get a velocity of 225 meters per second. For the suit, in the movie, the suit stops him and reverses his direction in approximately 1 second. So the acceleration needed to do that is negative 225 meters per second if we plug that into our v is equal to at plus v naught equation. All this won't actually work, however, because Stark Tower is only 347 meters tall, and if we plug in the time into our delta y is equal to 1/2 at squared equation, then we find that by multiplying 1/2, 9.8, and 23 seconds squared, the height of Stark Tower from how far Tony is falling is actually 2,592.1 meters, which is a lot higher than what it actually is. Since kinematics says that none of this would actually work, we'll see if energy makes it possible.
To start out, I want to say that I had to find the force required to break glass, and so I did some calculations, and I found it to be 6,650,000 newtons. And so that plus using momentum, I found that the velocity required to get the glass to break would be 358 meters per second. But in the real world, Nasser said that he actually went 2.5 meters per second, and so based off of my ideal work and force required to break the glass, I had to calculate the work done by Loki's arm to give enough work to break the glass. So in situation 1, to situation 2, K plus UG right here, because he has gravitational potential energy and kinetic energy running into the glass, plus the work that Loki did to throw him over there. I found the work to be 4,999,832.766 joules. That's a big number. But over here in the real, based off of the velocity that Nasser gave me, the kinetic energy plus the gravitational potential energy of his height from the ground is equal to 1,680.516 joules. And that's the work that was required by Loki's arm to break the glass. Okay, so back to ideal. After situation 2, when he breaks the glass, I found that he actually rotated and he rotated down and started falling like this until he finally stopped. But so I wanted to calculate the rotational energy that he had after he broke the glass, and so I did the initial kinetic energy plus the gravitational energy minus the work done by the glass on him is equal to the gravitational potential energy plus the kinetic energy, and I found it to be 4,997,000.628 joules. But then over in the real, his rotational energy is 949.715 joules. Okay, assuming no air resistance, when he falls and he starts rotating, he stops rotating and he just has kinetic energy at one point. And so I wanted to find the translational kinetic energy that he has after he stops rotating. And so I found the UGO plus KRO, equals KT plus UG, and the KT is equal to 5,030,143.33 joules. And in the real, his kinetic translational energy would be 34,092.417 joules. And then after he stops rotating and just starts falling, his kinetic translational energy starts getting bigger because his gravitational potential energy starts getting smaller. And since the energy is conserved between situations 3 and 5 because there's no work done, the kinetic energy has to compensate for the gravitational energy that he loses as he falls down the building. And so you can see that the numbers get really big. And same over here too. The numbers get bigger just because that's what has to happen in order for the conservation of energy to remain true.
So now the forces of the scene. Tony's weight was 77.2 kilograms, and so the force of gravity on him is 756 newtons. That was the first force. Second force of suit's propulsion to catch up to him. Force is mass times acceleration, so the mass of the suit was 109 kilograms, and the acceleration was 28 meters per second squared. So that gives you a force of 3,052 newtons. You have to subtract the force of gravity of the suit to find the force given by the propulsion. So that gives you a force of 1,984 newtons of the suit. Now the force of the suit's propulsion to stop Iron Man, that's also mass times acceleration. So the mass is 77.2 plus 109 to find the total mass times 225 meters per second squared given by Nassier's calculations. This gives us roughly 41,900 newtons. You have to subtract the force of gravity, which is 756 newtons. So that gives you a force of roughly 41,000 newtons to stop Tony. For comparison, a model rocket produces 30 newtons of force. And so this force is way bigger than that, and so there's just simply not technology enough for this to be possible.